When we consider approximations using linearization or tangent line approximations, one of the single most famous uses of that approach in science and technology is the approximation that sine x is approximately equal to x. Now, how does that work? Well, we pick a point. We're going to pick the point a equals 0 here. And when we do that, we consider our function to be the sine function. And if that's the case, then our derivative is simply the cosine function. And when we assess that at x equals 0, the function at 0 is just 0 itself. Sine of 0 is 0. Meanwhile, f prime of 0 is cos of 0, and that is equal to 1. So sine of x can be approximated by the function value 0 plus the slope value times x minus our initial point, 0. Again, here we're just using the same construction we have been using for our tangent line or linearization. And of course, most of these values disappear when we simplify, and we simply are left with x. So the graph of sine of x looks an awful lot like the graph of x, with the one caveat that the x values we're talking about are near 0. So this approximation is only valid when we imagine our sine graph, classical sine graph here, like so. The tangent line that we're talking about is very similar to the sine graph whenever we're talking about a range of x values fairly close to 0. So small angles is how it would be phrased in a lot of the language of physics, especially when you get to light and you're talking about refraction, things like that. The sine x approximately equal to x is heavily used there. Here's a little more detailed sketch of that relationship. I'm actually going to draw the tangent line on there first because we know how that's going to work out. And then if we do our graph, and I'm going to use the same scale. So remember that pi over 2 is approximately 1.6. So if we make this 1, 1.5, 1.6 would be out here. That should be where our peak is. Keeping the same scale on this side, that'd be a 1 around there. And so the graph we get for sine looks like that. And so it'll match the slope of this tangent line when we're close to the origin. All right, let's figure out actually how good this approximation is, though, for what kinds of angles. So here we have a table of x in radians. Notice when we took our derivative, and we said the derivative of derivative of sine was cosine, that was dependent on using radians for our measure. So everything we're doing right now has to be in radians. With that in mind, what we can do is we built a little table here of x in radians, and then the sine value, and then the difference between these two. If we're saying sine x is approximately equal to x, how different are those two things? We'll round things to 4 digits of accuracy after the decimal, and we can see that as x goes up, as the input goes up, then the error goes up as well. And what we're capturing here is, as we move further and further away from the origin, the difference between the straight line and the curved line of the sine graph, the gap there gets bigger and bigger. But on the plus side, it's not that big, and we're going to find out at what point the relative error gets bigger than 1%. You know, most of the time we're pretty happy with about a 1% error. So let's see how far along this curve we can get before we hit that threshold. So filling in these values, when there is no error, or it's so small we can't tell, there's 0 error. On the next one, to get the relative error, we take the absolute error over the exact value. So we always compare our errors to the true value if we can, and here the sine value is the true value. But actually, if we do that division, we get 0.002, reasonable approximation, or a 0.2% relative error. We're going to keep sliding along here and see what other values we get. Next up is 0.004. Then, not too surprisingly, 0.006. Actually, if you're round, it'll be 0.007. And then we reach the threshold of 0.001 or 1% relative error. So in other words, if we didn't want to use the sine function in our calculations and simply swapped out the sine value for the actual x value, so instead of sine of x, we used x, you can see there's a little bit of deviation here, and it's less than 1% error. Now, how big an angle is that? Most of us don't think in radians when it comes to estimates or visualizing things, so it's worth noting that that 0.25 radians, if we multiply it by 180 and divide by pi, is actually about 14 degrees. So if you're talking about the difference between, on a triangle, the sine of the angle and the angle itself, any angle that's less than 14 degrees, the sine and the angle itself will be within 1% of each other. So that's a reasonably broad range, especially with one of the classic examples of sine x approximating x, which is for a pendulum swinging. And typically we use that approximation to make the force calculations nice. And what this is saying is that as long as the swing is, 14%, 14 degrees rather, either way, you're fine. The error is going to be quite small. So that gives you a lot of leeway, say for a grandfather clock, to have the pendulum swinging back and forth and still keep accurate time, treating the forces with a simplified application of the linearization formula that we calculated using our standard formula from earlier. Now it's worth noting one last point, which is this at all true for degrees? So just going back a sec, if you are in radian mode and you plug in 0.25 into your calculator as x, and then do the sine of that, you in fact get basically 0.25 back. You get 0.2474, very close. However, of course, if you change to degrees, that goes downhill in a hurry, which is why we do not use degrees when we do these things. So if you have an x of, let's say, 5 degrees, sine of x is right off the bat, it can't be 5 because sine doesn't go that big. But if we do sine of 5 degrees, we get 0.087. These things are not even remotely equal to each other. Whereas if we had x equals the equivalent of that many radians, say 0.10 radians, it's around 5 degrees, and you do sine of x with radians, then you get a value that does match correctly. Sine of 0.1 is 0.0998, which is awfully close to 0.1. So these guys are a good approximation. If you're using degrees, this makes no sense whatsoever. So you just have to be very careful about the units, as always, in the calculations.